Hi everybody, this is Dr. Bricker here with Chapter 23, Part 2. Measuring voltage and current is where we'll start. So an ammeter is a device that measures current in a circuit element. So if you remember, current flows through wires, through resistors. So we want to measure the amount of current that is flowing through an element in a circuit. So we have to place an ammeter in series. So one of the labs that you'll do in person, we're actually going to measure current and resistance, so you'll get some experience with this. So it might look something like this. Here's the battery here. Current's going to flow this way, and then go through the resistor and then back to the battery. So negative side to positive side. So we want the resistance of the ammeter to be really, really small. We don't want the ammeter itself to be disrupting the circuit. Okay, so ideally the resistance of an ammeter would be 0. So when you measure current, you actually, using this kind of meter, have to break the circuit and insert the ammeter in the circuit. So practically speaking, at your house, usually what you're measuring is voltage. We'll see why in just a minute. Typically you don't want to break your wiring open and measure the current that way. It's more destructive. A voltmeter, on the other hand, measures the voltage across an element. So that's what's being shown here. Here's a 9-volt battery, resistor, 24-ohm resistor, and then to measure the voltage, you put the voltmeter across the element. So it's across this 24-ohm resistor. So in theory, this will have an infinite amount of resistance. You don't want any excess current flowing through the voltmeter. You don't want to disrupt the circuit. You just want to measure what's going on with the circuit. You don't want the meters to change what's actually going on. So this meter is in parallel with the resistor. You don't have to break open the circuit to do this. You just put the meter around this. Okay, so maybe you've measured voltage in your car or something like that. You didn't have to break any wires open. You measure the voltage across an element. Okay? So again, we'll get some experience with that with the lab. I just wanted to mention that to you. Okay, so then we can start talking about some more complex circuits. So here's a couple of rules of thumb, I guess. Two identical resistors in series, you just can add the resistance together. So the equivalent resistance is twice as much. In parallel, the resistance would be half as much. Let's take a look at this from last time. Okay, so in series, to get the equivalent resistance, you just add them together. So equivalent resistance, R1 plus R2 plus however many you have. So if R1 and R2 are the same, then the equivalent resistance would just be twice as much. On the other hand, in parallel, you have more paths for the current to flow through, if you remember. So the equivalent resistance you add like this, 1 over R1 plus 1 over R2 plus 1 over R3, etc. And then you've got to take the inverse of that. So, for example, if you wanted to get the equivalent resistance of, say you had two 10-ohm resistors in parallel, I could do 1 over 10 plus 1 over 10, take the inverse of that. So 1 over 10 plus 1 over 10 is 2 over 10. And then when you take the inverse of that, you get 10 over 2, which would be 5. Okay, so having two 10-ohm resistors in parallel will become 5. That's what this is saying here. So if you have the same kind of resistors in parallel, you've got 2 of them, the equivalent resistance is half as much. If you have 3, then it's 1/3 as much. We actually saw that on an example earlier. We had 3 15-ohm resistors in parallel. The equivalent resistance was 5. So these are just sort of helpful hints. These aren't on the level of, say, Ohm's law, but these are just kind of helpful hints to help us solve some problems. Okay. So resistor circuits, analyzing complex circuits. Definitely have to draw the circuit diagram, and then we want to try to reduce it to a simpler circuit. Why do we want to do that? Because then it just becomes this. The voltage of the battery is I times R equivalent. So we've taken a complex circuit and we've made it into something that looks like this. Okay. And the word simple circuit doesn't mean that it's easy. It just means you got one voltage source and and then one resistor, and then the current's going to flow like this. And then we can just use this formula. Okay, we have to get some practice with that. Okay, so step by step reduce to the smallest equivalent circuit until you just have a so-called simple circuit. Okay, so sometimes you'll have a purely series circuit, sometimes purely parallel, sometimes a combination of both of those. Sometimes you can't really reduce it any farther. It just takes practice. Okay, so this one is similar to 2337. So let's take a look at this problem in more detail. Okay, so here's the circuit. Current's going to come out this way. I'm just going to call this one I. And then it's going to split off. Part of it's going to go this way. Part of it's going to go this way. So let's call this one maybe I2. This one could be I1. And then it's going to come back together again. So I is equal to I1 plus I2 in this problem. Okay, that's just the Kirchhoff's junction rule. So in this problem, we want to figure out the current through each element. So really, we want to know I1, and I2. And then we want to figure out the voltage across each element. Okay, so let's take this more, complex circuit and make it not as complex. So this 10 ohm and this 10 ohm are both in parallel with each other. Current comes in, splits off, comes back together. So we can take the 10 and the 10 and get an equivalent resistance for that. We actually just solved that a second ago. So two 10s in parallel with each other become 1 5. So this circuit would become this. We've got still the same 10-volt battery. Now I'm replacing the 10 and the 10 with a 5. And then I still have this 5 ohm left over here. Okay, and then this is still the current coming out of the battery. Okay, so now I've got a 5 and a 5, and those are in series with each other. It's the same current that goes through each of those. So I could take this picture with the 5 and the 5 and replace it with this picture. I don't want to run out of room. So a 5 and a 5 in series becomes a 10. And then now I've got a simple circuit here. So I can get the total current from this problem. So I can use this. Right? The equivalent resistance of the whole circuit is just 10 ohms. Okay, so this over the equivalent resistance will give me the total current. So I've got 10 volts divided by 10 ohms, 1 amp. That's the total current. So all of these circuits are equivalent to each other. Okay, so this is 1 amp here. This is 1 amp here. This is 1 amp here. They're all equivalent to each other. Okay, so maybe we can figure out how much these individual currents are. So I know that this total current up here now is 1 amp. Now it encounters two resistors that have the same value, so it's equally likely to go down either path. So if this is 1 amp, each of those has to be a half of an amp. It's because this is 10 ohms and this is 10 ohms. So I1 has to be half of an amp. Okay, let me write it over here. I1 has to be 0.5 amps. Same thing with I2, because it adds up to 1 then. Okay, we also have to get these voltages. So let me call this like V2. V1. And let me call the voltage across this one V2. Now Ohm's law still works with all this stuff that we're doing. So V1 would be equal to I1 times R1. That's just from Ohm's law. V2 is actually in parallel with V1, so those have to have the same value of voltage. We could just solve it like this too, though, if we want to. I2 times R2. So when you put the numbers in there, this would be 0.5 amps times 10 ohms. So this is 5 volts. And this is also 5 volts, which it should be because they're in parallel with each other. And then let's see the voltage on this one over here, on the 5 ohm. Why don't I just call this one V3? V3 is equal to I times R3. Now that I is the total current. That's what comes out of the battery. That's what goes back into the battery. So this would be 1 amp times 5 ohms. So that's also turns out to be 5 volts. Okay, good. So you might say, well, you only have 10 volts to start with. If you add all these up, they add up to 15. If I do this plus this plus this, that's 15. Remember, that's not how voltage works. When you go around a loop, they add up to 0. So for example, I've got 10 volts here. This is 5 volts, and this is 5 volts. So if I go around this loop, it adds up to 10 volts. Okay, so be careful with that. When things are in parallel, they have the same voltage. They don't add towards the total. Okay, let's look at the next one. So actually, this one is the next one. We want to find the equivalent resistance for this circuit. Okay, so let's take a look at it. Let's see if anything's in series. This 10 and this 5, let's see. Yeah, this 10 and this 5 are actually in series with each other. The same current goes through each of those. So let me take this circuit and make it into something that looks like this. Here's the 5 ohm. This is a 10. This is 2.5. Okay, this one was 15. And now I can take the 10 and the 5 that I circled. A 10 and a 5 in series, you just add those together. This would be 15. These are all in ohms. I'm just not drawing the ohms out. Okay, so going back to the first picture here, nothing else is really, there's nothing else we could really do from the first picture. Nothing else is in series. Nothing else is parallel. So that was the only thing that we could do. Now looking at this second picture, the 15 and the 15 are actually in parallel. Current would come in, split off this way, and then come back together. That's what it means to be in parallel. The 2.5 and the 10 are not in parallel because the same current doesn't come back together through each of those. Okay, so the 15 and 15 in parallel, we could use that little rule of thumb. If you have two equal resistances in parallel, the equivalent resistance is half as much. So you would do 1 over 15 plus 1 over 15, which would be 2 over 15, and then take the inverse of it. 15 over 2 would be 7.5. So I could take this second circuit that I've drawn and make it into this one. We got a 5. This was 10. 2.5. And then a 15 and a 15 in parallel become 7.5. Okay, so I've taken this circuit and made it into this. And then you can kind of see a pattern forming. Now we have a 2.5 and a 7.5 in series with each other. So the equivalent resistance of series elements, you can just add them together. So this picture becomes 5. We got a 10. And then the 2.5 and the 7.5, just add them together. This becomes 10. And then we've got a 10 and a 10 in parallel, which we know that would become 5. So this 10 and this 10 in parallel become 5. And then we've got a 5 and 5 in series. Then you just add them together. So this one would just become a 10 ohm. Okay, so that's similar to one on the homework. Just work it step by step. Okay, let's see what's up next. So we've got capacitors in parallel and series. So we're going to put those into some circuits now. So a capacitor is a circuit element made of two conducting plates, as you know, with some sort of insulating layer. It could just be air. We've just used air-filled capacitors. So when you connect this capacitor to a battery, you actually charge it up. That's what's going on here. So eventually, the capacitor becomes charged. It takes some time for this to happen. It doesn't happen instantly, but eventually, when it's fully charged, the voltage on the capacitor is the same thing as the voltage that the battery has. And then you can carefully remove the capacitor and use that power for something else. I've got a flashlight. I turn a dial, I charge up a capacitor, and I can turn it on. It powers an LED, and it stays lit for quite a while, actually. So I'm using the energy that I've stored in the capacitor to do that. Okay, so we'll have series and parallel capacitors as well. Now they add just the opposite of series and parallel resistors. So in series, you just add the resistances together to get the equivalent resistance. It's the opposite for capacitors. In parallel, you can just add them together. In series, you've got to add them in that inverse way. So that's the opposite of resistors. Just be careful with that. Okay, so what you're about to see is the derivation of how that actually works. So here's a couple of capacitors in parallel. The charge that this one builds up is C1 delta VC, same thing here. Now these are in parallel, so they're going to have the same voltage. If we want to add up the total charge, we can just add them together. Right? We're just trying to figure out the charge on the capacitors, but the charge is C delta V, same thing with this one. So finally, you get Q is equal to C1 plus C2 times delta V. Okay, so if you wanted to take C1 and 2 and replace them with 1, you could do that. All you have to do is add them together. So in parallel, to get an equivalent capacitance, you just add them together. Okay, good. As it says here. Very good. And then the total charge, again, Q1 plus Q2, that's what would be on this capacitor. So the punchline to this whole story is, if you have capacitors in parallel and you want to get an equivalent capacitance, just add them together, as you can see here. So here's what happens in series. So a series capacitor have the same charge. So how this would actually work is, when you charge this thing up, in real life what happens is negative charge, I mean, conventionally speaking, positive charge moves, but let's just do it like in reality. So you've hooked this up. All right, now you've given somewhere for the negative charge on that part of the battery to go. This plate becomes negatively charged. Now this plate's negatively charged, so electrons on this plate don't want to be there anymore, so they flee to this plate. That plate becomes negatively charged, driving negative charge from this plate back to this side of the battery. What happens then is you can charge up a capacitor like this. I mean, we always think of conventional current, but really this is what's going on. Okay, and charge has spread out in this way. You know, negative charge doesn't like to be by other negative charge, and it'll spread out until you get to this sort of equilibrium condition. Okay, so this goes back to what we did with capacitors before. So Q is equal to C times delta V. So delta V is Q divided by C. Same thing here. Now in series, the voltages add up. So the voltage of the battery is going to be delta V1 plus delta V2. As you can see here. Again, our goal is we're just coming up with the formula for the capacitance. Okay? So that's going to be equal to the voltage of the battery. So when you put it all together, 1 over the equivalent capacitance turns out to be 1 over C1 plus 1 over C2. Okay? It really comes from this fact, that when you add these up, they add up to the voltage of the battery. Okay, so there we go. In series, you have to add them up like this. Remember, when you add up the equivalent resistance in parallel, you add them up in a similar way. Okay, this 1 over way of adding them up. Okay, good. So here's an example. Find the equivalent capacitance of the combination of capacitors in the circuit. What charge flows through the battery as the capacitors are being charged? Okay, so we want to reduce this to one battery and one capacitor. So what you see here are two capacitors in parallel with each other. So when capacitors are in parallel, you can just add them together. So a 5 microfarad plus a 1 microfarad, whoops, I can continue to the next slide. A 5 and a 1 in parallel, we can replace with a 6. Because in parallel, you just add them together. Now we have a 3 and a 6 in series. We've got to add them in that reciprocal fashion. Okay, and that's what's being done here. 1 over 3 plus 1 over 6. You could say, if you didn't want to use your calculator, you could say this would be 2 over 6 microfarads plus 1 over 6 microfarads. That would give you 3 over 6 microfarads. And then once you take the inverse of it, if you didn't want to use your calculator, you get 2 microfarads. So now we have a simpler circuit. One battery, one capacitor. Okay, so the battery sees a capacitance of 2 microfarads. The battery doesn't really care how they're arranged, but from the battery's perspective, the total capacitance is 2 microfarads. So if we want to figure out the total charge, go back to what we did earlier in the semester. Q is equal to C delta V, and we'll use the equivalent capacitance. Put it all together, and we've stored quite a lot of charge, 2.4 to the minus 5th coulombs. Okay, and then you've stored that. You could do something with it, hook it up to a light like I do when I go camping, and it'll stay on for quite a while until you have to physically recharge it. So RC circuits, I mean, we've done some work with capacitors and resistors now. There's also RC circuits. So there's circuits that contain resistors and capacitors. And it turns out, depending on the value of R and C, capacitors can take a long time to charge or not so long to charge, and we'll see how that works out. Same thing with discharging. Depending on the value of R and C, it could take a while for a capacitor to discharge. So here we've charged up a capacitor. Probably it was hooked up to a battery or something. It's got some initial charge. So that's what the 0 means there. Q naught is how it's pronounced. And it's got an initial voltage on it, which depends on how much charge we have. Okay, so this switch is open right now. So this has some voltage. Once we close the switch, then the capacitor could discharge through the resistor. Or maybe it's a light bulb you have there. Maybe it's a delayed wiper in your car, something like that. Okay, so once you close it, current's going to flow. So if you think about it, the capacitor is fully charged, and then once you close the switch, the capacitor starts to discharge. So discharge means charge flows through it. So the voltage on the capacitor is going to get less and less. So the current's going to get less and less. It's not a linear relationship, it turns out. So the voltage is not constant. Like a battery, the voltage stays the same. With the capacitor, the voltage drops off, the current drops off, as it actually discharges. The initial amount of current we have, though, is the voltage divided by the resistance in the circuit. That just comes from Ohm's law. Okay? And so this kind of is what I've said, a time later you have less current because you've got less voltage on the capacitor. Okay, eventually it completely discharges. Here's what the current actually looks like. It starts at its initial value and then drops off, this exponential drop. Same thing with the voltage on the capacitor. It follows this pattern. Okay, and this is what it actually looks like. So it's this Euler number. That's what the E stands for here. So the current that you have at some amount of time is equal to how much you started with, and e to the minus t over RC. And then the amount of voltage you have is the amount of voltage that you started with, and then e to the minus t over RC. So in your calculator you have the e, you've got the e on your calculator. It's called Euler's number. You're taking this e and raising it to some power. So think back to what you did with natural logs, and then maybe that'll ring a bell if you haven't used it in a while. Okay, good. So this R times C value that you just saw is called the time constant, and sometimes it's replaced with this symbol tau. So instead of writing RC every time, sometimes people put tau in there. So the units of tau are actually seconds. Okay. Okay, so these are for discharging a capacitor. It's somewhat different when we look at charging a capacitor. The only other thing I could add to this really is Q, remember, is equal to C times delta V across the capacitor. So if you wanted to, instead of writing this in terms of voltage, you could write it in terms of the amount of charge that you have. Because delta V on a capacitor, I guess I could just leave it like that actually. Well, let me change it. Q over C is equal to delta V across the capacitor. Let me just put the little O there to emphasize that's the initial amount. I'll do that same thing with the charge here. So if you want, you could take Q over C and plug it into this formula. You know, on the left-hand side and on the right-hand side, take Q over C, plug it into the formulas. The C's cancel out, so then you get this, the amount of charge that you have at a certain amount of time, it's just a function of time, is equal to how much you started with, and then e to the minus t over RC. Okay, so if you wanted to, you could figure out the amount of voltage on the capacitor and then figure out the charge, because the charge is C times delta V. Or here's another formula for you right away. Okay, good. Again, this time constant is RC. You just saw that a minute ago. And then the only other one I would add here is the charge one that I just showed you. So here's an example. The current, or no, maybe it's not an example. The current and voltage in a circuit do not drop to zero after one time constant. It takes a certain amount of time to drop to zero. You saw the graph of what it actually looks like. So each increase in time by one time constant causes the voltage and current to decrease by e to the minus 1. Right? If you have one time constant, going back to this formula, one time constant, if the time is equal to one time constant, you have e to the minus 1. So if t is equal to RC, in other words, it drops by 0.37 or 37%. So here's 37% after one time constant, and then 0.13, etc. This would be after two time constants. For all practical purposes, after 5 time constants, you're down to 0. Okay, so this is exponential decay. So if you've seen that in other subjects, this is where it comes from. Okay, so time constant is R times C. Large time constants, a higher resistance, in other words, or a higher capacitance, you'd have more voltage then. It takes a longer time to discharge. Okay, so the bigger the time constant, the longer it will take to discharge. And here's a quick check. The following circuits contain capacitors that are charged to 5 volts. Okay, so they all have 5 volts. All of the switches are closed at the same time. Okay, so these are capacitors that are charged up. After 1 second, which capacitor is charged to the highest voltage? So in other words, which one of these situations has the largest time constant? Which one has the largest R times C value? All right, let's just quickly calculate this. 2 times 1, that would be 2. 2 times 0.47, that would be something like 0.94. This one would be 3. This one would be 3 times 0.47. So roughly a little bit less than 1.5. So to me, this one's got the largest time constant, so it's going to have the largest amount of voltage still left on it. Okay, and that's true. Okay, so it comes to, the way I got that was which had the largest RC value. Okay, good. Let's look at this. So this is a way that you could actually construct this. So you first have this here in position A, and you charge up the capacitor. If it's fully charged, it charges up to 9 volts. And then when you take that switch and move it over to B, then you can actually discharge it through the capacitor. When you're charging it, the 10 ohm resistor is not part of the circuit, right? There's no closed path going through the 10 ohm resistor. And then when you move the switch over to position B, now the battery is out of the equation, and you're just discharging the capacitor through this resistor. Okay, so let's read what it actually says here. The switch has been in position A for a long time. That means it's fully charged. Okay, good. The switch is then changed to position B at 1 second. What is the current in the circuit immediately after the switch is closed? And then what is the current 25 microseconds later? Okay, so if it's fully charged, the initial voltage on the capacitor is 9 volts. So as soon as you close it, you have 9 volts, you have 10 ohms, you could figure out the initial current. And then that current's going to decay exponentially. We'll have to use our new formulas to figure out how much current we have 25 microseconds later. Okay, so there's the initial current, 9 volts divided by 10 ohms, so 0.9, and then it decays exponentially. Not in a linear way, exponentially. But here's the formula. We're going to need tau, first of all. So tau is 10 microseconds. And then, okay, 10 microseconds, that's what tau is. And the amount of time they're telling us is 25 microseconds. Okay, so we have about 2.5 time constants, 2.5 multiples of 10 microseconds. Okay, let's see. Maybe when the switch is closed, the initial current, what is the current in the circuit? So we'll have to use that formula. I guess I don't have it written down here. Okay. All right, so we'll actually have to put the numbers in for that one. So I don't see it there. Okay, so here's the formula that we need. I as a function of time is how much current you start with, e to the minus t over tau. So the amount of current that we started with was 0.9. So 0.9 amps. And then e to the minus, and it's 25 microseconds divided by 10 microseconds, right? That's what tau is. And I didn't write microseconds because they're each in microseconds, so I know it's going to cancel out. Okay, so when you put that in your calculator, let's see what we get. Okay, so I did 0.9 e to the minus 2.5 because 25 over 10, and I get 0.074. 0.074 amps. Okay, very good. So what we've done so far is discharging a capacitor. The formulas that we have were for discharging a capacitor. They're similar, but not exactly the same formulas for charging a capacitor. Okay, so this is how you might actually do it. Here's a battery, a resistor, a capacitor. So when you first close the switch, the capacitor doesn't have any voltage. So in the beginning, the current just comes from Ohm's law again. So the initial current is this. I'll write 0 for initial. The initial current is just the voltage divided by the resistance. But you start charging up the capacitor. And then when you charge up the capacitor, it opposes the current, right? That's plus to minus. This is plus to minus. So initially there's no voltage on the capacitor. You close the switch, the capacitor starts to build up a voltage that opposes the battery. So the current gets less and less. It starts out at this value, and then it gets less and less. The voltage on the capacitor, on the other hand, starts out at nothing and then builds up to its value. Both of those events do not happen linearly. They happen exponentially. When the capacitor is fully charged, it has the same voltage of the battery. But in the beginning, it has no voltage. So here are the formulas for charging a capacitor. The current one's the same. We start out with our initial value, and you just saw this, the initial current, and then it drops off. Okay? The voltage on the capacitor, on the other hand, formula is different. Okay? Well, let's see if it makes any sense. What happens when t is equal to 0? So when t is equal to 0, I'm just saying, let's see if this makes any sense. E to the 0 would give you 1. So 1 minus 1 would be 0. The voltage on the capacitor starts at 0 and then builds up to its final value. When the amount of time here gets really big, e to the negative big number becomes 0, and then this term would be 0, and after a long time, so then we build up to the voltage on the capacitor. So the formula makes sense with what I've said. Initially, no voltage on the capacitor. Eventually, the voltage of the battery. Okay, so this is for charging a capacitor. So let's see what we have here. Okay, so this would be charging a capacitor, right? You're taking a battery and you're charging a capacitor. The capacitor is initially uncharged. Immediately after closing the switch, the capacitor voltage is, well, it's 0, right? That's what it has to start off at. That's just the way it works, 0. Okay, so it's not charged at all. And then eventually it will build up to the voltage on the of the battery. Okay, we don't know what that is in this problem actually. Okay, so the rest of these slides are just a summary of the chapter. Good, so that's really chapter 24, sorry, 23. 24 is about magnetism actually. So this electricity stuff, it can be kind of confusing. There's not a lot of intuition. Maybe out of everything we've done this semester, it just takes a lot of practice with these problems. Okay, talk to you soon.